The last section of chapter 3, polynomial and rational inequalities. So we've been talking about polynomials and rational functions the whole chapter. And now we're just going to do a couple examples of like one extra step, which is taking them and solving an inequality. So typically this means you're going to have some sort of greater than, less than symbol, possibly an equal to symbol. And your job is just to find out the values of x that make it true. So for example, here's an example of a polynomial inequality. Your job is to find out when is this thing on the left-hand side greater than or equal to 0. And when you're given a problem like this and asked to solve it, notice we're giving our solution an interval notation. Your first step would be to bring everything to one side. If you can have one side equaling 0, or your inequality, and then 0 on the right-hand side, you're going to be in a lot better position for things that you can do. So I'm going to bring everything to one side, 0 is going to be on the other. I already have that with this example, so that's great. The second thing I'm going to do is I'm going to factor. So if you want, you can pause and try to factor this polynomial on the left-hand side. And there's a couple reasons why I do this. So one of them is I want to know when this inequality is equal to 0. No matter what inequality I have there, I want to know when is the left-hand side going to be equal to 0, because that is the place, those x values are where it's going to change from being positive to negative. So I do that, and you can see that that's going to give us that either x squared equals 0, x plus 3 equals 0, or x minus 2 equals 0. And if you want, if I don't want you to get confused, I can change this to a 0, or an equal to, equal to 0 there, just to show you that one step I want to do. So besides bring everything to one side, my second step is then to factor. So we find that really kind of critical values, important values to us, are going to be these 3. They're going to be so important that I'm going to put them on a number line. And what should hopefully be pretty apparent to you is that when I plug in those values, it makes my inequality equal to 0. And since I want to know what values make the left-hand side greater than or equal to 0, these 3 values make my inequality true. So understand that when I plug in -3, I'm going to get 0 on the left-hand side. Is 0 greater than or equal to 0? Yes. So x equaling -3 gives me a true statement in my inequality. So I'm going to put a T there. True means that it needs to be part of my solution. Anything that is true is going to be part of my solution because it makes the inequality true. Now, a couple different ways you can go about this. If you want, with what I have there, you can make intervals, test point substitution. You could also do it, by just testing values, putting them on your number line there at the top. Kind of as you get quicker, you may decide to make changes to how you do it. So we want when x is less than -3, so that's this interval here. Then we want when x is greater than -3, less than 0. So that's in here. We want when x is greater than 0, less than 2. That's here. And we want when x is greater than 2. And by testing values within those intervals, we can put them into our factored form of our polynomial on the left-hand side and say, hey, is it greater than or equal to 0? Because if it is, then that makes it my inequality true and needs to be part of my solution. As you can imagine, there's many, many values that are going to make this greater than or equal to 0. So we just need to find which ones those are. So let's put in, for example, x equaling -10. And again, you don't have to worry so much about what the actual value is. Your job is just to say, is it going to give me positive or not? So if we plug in -10, notice that first factor, we have an x squared. Everything that comes out of that is going to be positive. The next factor, x plus 3, when I put in -10, is going to give me a negative. And when I put in -10 to x minus 2, that's also going to be a negative. A positive times a negative is going to give us a positive. That means that any value that is less than -3 when we plug it in is going to give us a positive number, and therefore makes our inequality true. So we already know that part of our solution is anything from -infinity all the way up to -3, including -3. So I'm going to put a bracket there to hold on to that -3. Then we are going to test something between -3 to 0. So maybe I test, for example, -1. I put those into my 3 factors that I have there on the left-hand side. So I will have positive, as always, positive, and negative. This is going to give me a negative. That tells me, oh, any value I put in between -3 and 0 is going to give me a negative value. Well, I want when it's greater than or equal to 0, so that's going to be false. Then we could put in 1, and it looks like we'll have positive, positive, and then another negative. So this is again negative, so also false. So these 2 intervals are false, but don't forget that 0 makes it true. So we get to just put in this one set of x value being 0, because 0 does make it true. So I got to put that in there somehow. So that's how we would put that. We have an interval union with the value 0, because 0 makes it true. And then false on either side of 0, so we can't include those. And then something greater than 2, I'll pick 10. I will always have positive here. I will have positive here, and I will have positive here. That's going to give me positive values, anything that's greater than 2. So that's going to be true. True. And therefore, I want to include that in my solution. So I'm going to union with the interval 2. Now notice 2 makes it true, so I'm going to include 2 all the way up to infinity. And not up to infinity, but I'm going to put infinity there to show that anything greater than 2 is going to make this inequality true. And that's our solution in interval notation. Now, for rational inequalities, it's still very similar. But we want to think about values that make our inequality, we're still looking for whatever values make this inequality true. The best thing to do is still to bring everything to one side. So I'm still going to have it with a 0. So -4 minus x plus 3 is going to be greater than 0. So that's what I want to be true. The best idea is to combine it into one fraction. So I'm actually going to add these 2 fractions together by giving them a common denominator. I got to think about trying to maximize my space here. I'm going to give them a common denominator. So that's going to be 7 minus x times x plus 3 minus 4 minus x times x plus 1, which is going to be all over x plus 1, x plus 3. So just, again, just combining them there. So that my goal here is I need to find out when this left side is equal to 0 or when the left side is undefined. So we have that extra layer because we have rational stuff. I have to think about when I might have something that's undefined. We don't have to think about that with polynomials, smooth and continuous. But rational, yes, we got to think about anything that could make us undefined. So now we're going to combine things. Again, I have to be a little bit careful with my space because of where I'm going to put my head here, but I guess I'll try to do, okay. So if we multiply this out, just know that you're going to have a negative x squared and a plus 4x minus, plus 21, and then minus 3x plus x squared minus 3 over that denominator. Whoop. Okay. Okay. and we want to know when that's greater than 0. And then if you simplify, fun part, you simplify what you have in your numerator there, you're going to get x plus 17. Again, I'm just putting this in a slightly different space so that I can make sure to have space for myself. So it's going to look like this, the combining of the like terms. So it really kind of simplifies this. So I want you to understand that the values that make this top piece true, this thing that we started with here. So the values that make this true right here are the same values that make this true. It's true. It's true. Because all I did was rewrite it. I just used, everything was math legal. I just rewrote it by combining the fractions, and now we have this one fraction finding out when it's greater than 0. So once we've done that, now we just want to think about what values could make this 0 or undefined. So I want you to notice that the only value that would make this 0 would be a negative 17. Because it's going to make the top 0, the bottom's going to be something else, but 0 divided by anything that is not 0 is 0. We also have to think about the fact that x cannot be negative 1, negative 3. That those are going to give you something that's undefined. They cannot be part of our solution. And then just like we did before, we just create our little number line here of our values, and we look at our intervals. And we can put those values into where you see number 2 there. So here's going to be our number 3. We're going to test some values. So I'll do this a different way. All I'm going to do is test some values. I'm not going to use my table, but if you like the table, you can use the table. If that works out well for you, that's fine. I want you to understand that I already know that these two values are false. They make this inequality undefined. That can't be part of our solution, so it's got to be false. For negative 17, you should understand, makes it equal to 0, but we want greater than 0. We don't have an equal to sign in our inequality, so negative 17 can't be part of our solution either. But now we can test values. So a slightly kind of more straightforward way would just be to say, I'm going to pick something less than negative 17, like negative 20. It's going to make our numerator negative. It's going to make our denominator a negative times a negative, which is positive. So we're going to have negative divided by positive. That's going to be negative. And because we want to be greater than 0, that is false. We can pick something in between negative 3, negative 17. Let's go with negative 15. My numerator is going to be positive. My denominator is going to be negative, negative. So that's a positive divided by a positive, or positive. So that is, positive values are greater than 0. So that makes my inequality true. Here, maybe I'll pick negative 2. When I plug that in, my numerator is positive. My denominator has a negative times a positive. That's going to be a positive divided by a negative is a negative. So that is false. That is not greater than 0. And something that's greater than 1, let's get crazy. I'll pick 50. My numerator is going to be positive. My denominator is going to be positive, positive. Everything's positive there. That is greater than 0. Positive numbers are greater than 0, and I have true. So our solution now is simply any of the intervals that are true. Notice I'm going to need parentheses here because I'm not including any of my endpoints of these intervals because they do not make it true. So I'm going to start with negative 17 to negative 3, and then again from negative 1 up to infinity. So notice that is, we're talking about this interval right here, that's the interval, and this interval right here. And that's how we came up with the values that we did. If you want, you can kind of see, and maybe I don't do the arrows because I'm gonna, stopping them, stopped it. But that's the idea, is that it's here to here in between. So the idea, just any value, any x value in between those values in my intervals are going to make that inequality true, and thus are part of our solution. And that's section 3.7.